So we're going to be looking at the first case, what I think is the most difficult case to get the answer to, and that is the imaginary solutions. So when b squared minus 4ac is less than 0, right? It doesn't mean that we have no solutions to our ODE. It just means that we have imaginary solutions, and we can still solve those. And deriving this is a little bit tricky, but once we actually have the derivation, it's pretty much just plugging them into an equation and solving. So let's get right into it, okay? First thing that I'm going to do is I'm going to notice that I can rewrite b squared minus 4ac, the square root of this. This is the same thing as if I were to multiply -1 times 4ac minus b squared, right? We also know that when we are multiplying two things underneath the square root, we can break them up, right? So we can take this square root of -1 and we can rewrite it as I, right? So this is going to be equal to square root of 4ac minus b squared times our imaginary number, okay? And just bear with this manipulation, right? It's just a derivation. So, okay, let's write this out. So now we've got r is equal to minus b over 2a. I'm going to rewrite this, plus or minus, and this will now be the square root of 4ac minus b squared times I all over 2a. Okay? So let's just do a quick little simplification here. Let's say, let me make some space. Let call alpha be equal to minus b over 2a, and beta will be square root of 4ac minus b squared over 2a. Okay? Awesome. So what can we do now? We know that because of the quadratic formula, we know that one solution will be alpha plus beta I. Our other solution will be alpha minus beta times I. Okay? And I know this is still all in variables, but just bear with me. We're going to follow through with this. So if I were to write the solution, right, we know that y is equal to e times rx, but we have more than one solution for r, right? So when we have multiple solutions, what we need to do is actually take a linear combination of our solutions to get a general solution for everything, right? So our general solution for this will be y is equal to, and let's call it capital A, times e to the alpha plus beta I times x plus b times e to the alpha minus beta I times x. Okay? And I'm just going to rewrite this once again as y is equal to a times, this will be e to the alpha times, alpha x, sorry, times e to the beta x times I plus b, and this is multiplied by e to the alpha x times e to the beta x I. Oh, and that should be a negative beta x, right? Okay, perfect. I think this is all looking good. So you'll notice that we can factor out an e to the alpha x. So let's go ahead and factor that out. So this will be y is equal to e to the alpha x times a e to the beta x I plus b times e to the minus beta xi. Great. And we could leave it in this form, but most commonly you're going to see this expressed a little bit differently. And we're going to be expressing it using cosine and sine. So if you'll remember back from our linear algebra days, we know that e to the theta times I, well, that is just equal to cosine times cosine of theta plus I times sine of theta, right? This is just polar form to exponential form, right? Okay, I'm just going to move that to the side. Okay, perfect. So let's express this differently now, okay? We're going to express this as, okay, e times alpha x, and then in brackets here, I'm going to have a times, and then this e time, this is all multiplied by cosine of beta x plus I times sine of beta x, okay? Plus, and remember, this is just this first part here, okay? Now with this second term, oops, I'm going to have to move this down a little bit. Okay. So now this will become b times cosine of negative beta x plus I times sine of minus beta x. Great. Okay. So another quick substitution that we're going to do here, we're going to remember that sine of minus beta x is actually equal to minus sine of beta x, right? Okay, great. We also know that cosine of minus beta x, this is going to be equal to cosine of beta x, right? These are just some trig identities that we know. Okay. So if we were to simplify this, we could factor out our cosine of beta x, and so we got e to the alpha x, and this is cosine of beta x, and then we're multiplying this by the quantity a plus b, right? Because we just turned this guy in blue, we just turned that into cosine beta x, so we've got a plus b, right? Okay, a plus b cosine beta x. Great. And we are going to add this to, okay, well, if we have sine of beta x and we're turning that into, if we have sine of negative beta x in our green term, then to get it, so in order to factor out sine of beta x, we need to take out that negative, like that, by using that trig identity. So this will leave us with sine of beta x times, and this will be a minus b, and this is also multiplied by our imaginary number. We cannot forget that. Great. So we've done pretty much all of the ugly parts, okay? And now what we're going to do is, well, we know that a plus b, that's just a constant, right? So let's just make it way easier to view. So let's say let c1 equals a plus b, and we're going to let c2 be equal to a minus b times I, right? So with these constants, we can simplify our general solution to have all real and imaginary solutions here. So e to the alpha x times c1 times cosine of beta x plus c2 times sine beta x. And just a reminder, this is where alpha is equal to minus b over 2a, and beta is equal to 1 over 2a times the square root of 4ac minus b squared, right? So this here is kind of the solution that we could jump to when we're given an ODE and we find that its auxiliary equation has imaginary solutions.